Good morning everyone. So welcome back to our continuation session on electric field intensity due to line charge density. So we are talking about second case where we are considering infinite line. So we have infinite line on z-axis. It is extended from positive z-axis towards negative z-axis up to infinity. So last session we have seen we have source on z-axis. It is applying electric field intensity on a point which is available on floor. For that we have used the formula of differential electric field intensity which we derived from Coulomb's law. Then we discussed about the distance vector r bar. It is nothing but destination points minus source point. From that we have calculated unit vector ar cap, which is equal to r ar cap minus z az cap divided by square root of r square plus z square. Now we have to keep this direction value into the total vector E bar. So now I will erase this part and then I will put the values and we will continue the derivation. So until then you just wait for a while. So I will just pause it. Now here we will take the value of differential electric field intensity, which is equal to rho L dz by 4 pi epsilon naught r square. But r square we have right now calculated, it is the mod of r square is square root of r square plus z square. So we have r square, so directly we can write here r square plus z square in place of r square. So this is the position vector value we have kept here. Along with that we have to keep the value of ar cap, which is nothing but r cap minus z az cap divided by square root of r square plus z square. Now we have to integrate this term in order to get the entire electric field intensity applied due to the infinite line. So we will take integration of this part, so we can remove this differential part. What will be the limits? Limits are from minus infinity to plus infinity. So we will take out the constants. What are the constants here? The constants are rho L by 4 pi epsilon naught. Rho L by 4 pi epsilon naught is a constant that we can take out. One more thing we have to see here, r ar cap minus z az cap. These two terms now we will discuss. Our charge is present on positive z axis. That means the differential length which is on differential z surface is having differential charge dq and it is applying some differential electric field intensity d. Whenever there is charge present on a positive axis and if same line is extended in opposite direction, then there will be presence of equal and opposite charge at the negative side. So like this, if we have this plus dz, there will be minus dz. So charge, equal and opposite charge present at the negative side will cancel the z component. So z az cap term will be cancelled because it is present on positive as well as negative term. So it will get cancelled. We will take out the constants and we will rewrite this expression. So we will get the expression as E bar. So our constants are say rho L divided by 4 pi epsilon naught integration of dz by r square plus z square into, here we will take one r cap divided by r square plus z square. So this whole term is a complex term. So we have to consider substitution to solve this one. So let us consider z is equal to r tan theta. if we keep z is equal to r tan theta, then dz will be r secant square theta d theta. Now we are using substitute, so the limits will change. Earlier limits are from minus infinity to plus infinity. If we keep in place of theta, the new limits will be from pi by 2 to minus pi by 2. So now we have to solve this expression by keeping these new values. So let us keep this new value here. We will get, say, E bar is equal to rho L by 4 pi epsilon naught. The new limits are minus pi by 2 to pi by 2. So in place of dz, we can write r secant square theta d theta. So it will be r secant square theta d theta into r ar cap. So here we will get r square plus, in place of z we are keeping r tan theta. So it will be r square plus r square tan square theta. So now if we multiply these two terms, this r square plus z square into square root of r square plus z square, it will become the whole to the power 3 by 2. So all the terms are included. Now further we will simplify it. So here we can see that we have 2 r's, so it will be r square. From here we can take out one r square common. So this r square common, in bracket we will get 1 plus tan square theta. 1 plus tan square theta, we can write it as secant square theta, and the whole 3 by 2 will become secant cube theta. So this secant square theta will get cancelled. So this simplified expression I will write down. I will just erase this and I will note down the expression. So I will just pause it. So now this is the simplified expression. We have reduced this expression to this expression. So what we have now, we have E bar is equal to rho L by 4 pi epsilon naught integration of 1 upon secant theta d theta. So direction is AR cap. So 1 upon secant theta is sin theta. So here we can write rho L by 4 pi epsilon naught sin theta. The limits are from minus pi by 2 to pi by 2. So it will be minus 1 minus minus 1. So it will become 2. So if we get this 2, we will get one r term here. We will take it out, r here. So this sin theta, if we put the limits minus pi by 2 to upper limits, lower limits, we will get 2 here. So 2 will get cancelled. So it will become rho L by 2 pi epsilon naught r. So this is our electric field intensity due to infinite line charge. So what is the difference between earlier expression? Earlier for point charge, electric field intensity was q by 4 pi epsilon naught r square. Now we have one expression for point charge, one expression for infinite line charge. Now this case is for line charge. Now we have to consider second case where we will consider surface charge. Now in this case surface will be distributed and that surface will apply some electric field intensity in surrounding region. So say this is my surface and I will consider only one plane, and this plane is full of charge, and the charges placed on that will have some force line going out in the surrounding region, and there may be some point placed in the space. So how much force is applied from this entire surface on given point P is part of our calculation. So in this case we have to replace line with surface. On any one surface we will consider the charges distributed. Now I will just erase this and we will continue. So we will consider our surface on the floor and point destination on this line. So in place of source we will have destination, in place of destination we will have source. Now we are considering electric field intensity due to surface charge density. So again we will take 3 coordinates as reference. So we have say these 3 coordinates for our reference. Vertical is z-axis, the line below this board is y, the line coming towards us is x. So we have x, y, z, 3 axis. Now we have to consider the source who is applying electric field intensity. So let us consider that this electric field intensity is placed on the floor. So like a paper, plain paper, it is on floor. The entire floor we are considering as the source of charges. So what we say, there are charges present on this particular floor. Say this is xy plane. Xy plane, or which constant plane it will be on floor? What will be the value of z? The value of z will be 0. So it will be called as z constant plane, and values of x and y are changing. We have discussed it in the coordinate systems. So it is called as z constant plane or xy plane, where values of x and y are changing. So this is plane where all charges are present. Say this is our surface S. So from this we will consider small differential surface ds for mathematical purpose. The small differential surface will have small differential charge dq, and he is applying some small differential electric field intensity d. These values we are using for mathematical calculation. Once we have the formula, we will calculate it by using integration for the entire surface. So this is our source. Destination point we will consider on z axis. So say this is my point P, which is destination point. What will be the point location here? So if we consider cylindrical coordinate system, radius will be 0. The angle will exit say phi, and there will be some height z. So this will be the destination. Now this source is applying some force on destination. So we will show arrow from source to destination. What is this arrow for? This arrow is representing position vector r bar. And how we calculate r bar? R bar is calculated as destination points minus source points. So we have seen what are the destination points. So what are the source points? Source points, here for this place there will be radius. So there will be r, there will be some angle phi, but z is 0 here. So it will be r comma phi comma 0. These are our source points. So what will be r bar in this case? R bar in this case will be first term, say 0, destination minus source. So 0 minus r, so it will be minus r ar cap. Then phi minus phi, it will be 0. Then z minus 0, it will be positive 0, so it will be plus z az cap. So this is our r bar. What will be mod of r bar? Mod of r bar will be square root of r square plus z square. What is next step? To calculate the direction component. For this direction component is given by ar cap. Ar cap is equal to r bar divided by mod of r bar. So it is nothing but r ar cap plus z az cap divided by square root of r square plus z square. So these are our prerequisites we require. Now one more thing you can see here. Now earlier this should be minus. Earlier in previous example, the charge, source charge was present on positive z axis. So equal and opposite charge we considered on negative z axis, and the z component was cancelled. Now dq is present on this z constant plane with radius r. So with equal radius at opposite side there will be equal and opposite charge. which will cancel this term. So that we have to consider in derivation. So what is our next step? Now this is the line, it is applying some differential electric field intensity dE. So what is basic formula of dE? We derived from Coulomb's law. From Coulomb's law we derived that, say, E is equal to Q by 4 pi epsilon naught R square. If it is E bar, we have to take AR cap. Now here we are considering small differential E, dE bar. So there will be small differential charge dQ. So what is this dQ value? This dQ, here we don't have a single charge. We have the density of charges. We are considering that there are number of charges equally distributed. So this surface is considered as uniform density surface. The density of charges is same. Everywhere number of charge distribution is same. So how we calculate this? Charge density is given by rho s. So if we take out here rho s for any density, last time we have discussed the simple formula cos per surface area. Cos of charge density is nothing but charge. If charge is dq, it will be dq, and inversely proportional to the surface area ds. So from here we can say that what is, if we take dq is equal to, what will be dq is equal to, dq will be equal to, we will shift this term to LHS, so it will become rho s ds. So value of dq we can keep here. So what will be the expression here? It will be now dE is equal to, in place of dq we will have rho s ds divided by 4 pi epsilon naught R square into AR cap. Now one more thing we have to discuss here. What about this ds? We discussed about coordinate system to use it in the derivations. Now this differential surface where the entire charge is present on xy constant plane. So this differential surface is given by, say, ds, where z constant plane. So we will write it as dsz. So this dsz is product of remaining two terms. What are remaining two terms? One is phi term, it is given by r d phi, and another one is, one z is gone, so it will be r d phi dr. So in sequence we will write it as r dr d phi. We can keep this value of ds in place of this expression. So we will get d bar is equal to rho s into r dr d phi divided by 4 pi epsilon naught R square. Now in place of AR cap we can put this value. So here we will have minus R AR cap plus Z AZ cap divided by square root of R square plus Z square. So this is our expression. Now we have to simplify it in the similar manner. If we take integration of this term, what we will get? We have to take integration here. So we have to take now double integration, because this is surface. For line there was single integration. For surface we will have double integration. So which two terms we have to use for double integration? One is for dr, another one is for d phi. So what are the limits for radius r? The limits in cylindrical coordinates for radius and angle phi. Angle phi rotates from 0 to 2 pi. How we calculate r? R we calculate from, say, origin 0 to infinity. So we have to use these limits. So here we will have one limit which is r equal to 0 to r is equal to infinity. For another one is phi is equal to 0 to phi is equal to 2 pi. Now your work is to keep these values in this particular integration, solve it and answer your final expression in the comment. And while listening the class, you can make short notes, type it in the comment, post along with this, solve this expression and put the answer in the comments. Till then, have a good day.